Why are electric fields so hard to understand? Imagine trying to see an invisible force stretching across space, guiding charged particles without touching them. That's what makes electric fields so tricky to grasp. They are like unseen winds that push and pull, but we can't see the wind itself. Instead, we see what it does. Electric fields are regions around charged objects where other charges feel a force. The strength of this force depends on how much charge there is and how far away it is. The farther you go from the charge, the weaker the force becomes, following what's called an inverse square law. This means if you double the distance, the force drops to a quarter of what it was. Now think about the idea of a field. It's not just a simple line or a shape you can hold. It's a concept that spreads out in space, describing how the force acts everywhere around the charge. To understand this, scientists use vectors, arrows that show both how strong the force is and which way it points. Visualizing these vectors helps, but it's still abstract because we can't see the field itself, only its effects. Mathematically, electric fields are described with complex equations. Coulomb's law explains the force between two charges, but when things get more complicated, like moving charges or changing fields, Maxwell's equations come into play. These are advanced equations involving calculus that describe how electric and magnetic fields interact. They are not simple to picture or solve, which adds to the difficulty. Electric fields are also connected to magnetic fields, forming what's called the electromagnetic field. When charges move, they create changing electric fields that can induce magnetic fields, and vice versa. This interconnectedness makes understanding electric fields even more complicated because they don't exist alone. They are part of a larger dynamic system. To help us understand electric fields better, scientists use electric field lines. These lines start on positive charges and end on negative charges. They never cross each other, and their density shows how strong the field is. But these lines are just a simplified picture. They help us visualize but don't fully capture the real behavior of the field, especially when charges move or when the field changes over time. In everyday life, electric fields are everywhere. They power our electronic devices, cause static electricity, and trigger lightning. Still, because we can't see these fields directly, they seem mysterious. We're relying on their effects and mathematical models to understand them. So, the reason electric fields are so hard to understand is that they are invisible forces that spread out in space, described by complex math, and linked to magnetic fields. They challenge our senses and our minds to think about something that's not directly observable but has a huge impact on the universe around us.